We are the Lita Foundation. We're building the Valida ZK VM. We're using it to push the performance and usability of zero-knowledge proofs. So here are our recent benchmarks. We just ran these. Jolt came out while I was giving this talk last time, a month ago, so it was very exciting to try to see how that changes the competition right now. So here is a measurement in terms of wall clock time, so that means how long it actually takes to run the computation, including the use of many core machines. So we're up to hundreds of times faster than some of the leading options, and even maintaining that edge against Jolt, which came out and really surprised everybody with how great their performance is. This is another metric on SHA-256. I guess we don't get quite as much of a boost on that one. So the thing with these benchmarks is that they are somewhat dependent on the type of computation being proved. So you really want to run them on a whole lot of different things. So I think somewhere that Valida really shines, though, is not so much the proving time, but the proving efficiency. So that's like the proving time if you had to use a one-core machine, or the number of CPU cycles needed. It's a reasonable metric for how much you're going to spend financially to make the proof, or how much energy you're going to consume. And this is, so we ran this benchmark on computing Fibonacci numbers, and we have, what is this, 1000x speed up. Okay, so all right, here's table of contents. I don't really have anything to say about that. So motivation. So what is a ZKVM? What do we want to do with it? We want to prove succinctly, so it should be easy to check the proof, and in zero knowledge, meaning that you don't reveal any additional information about any intermediate objects. And what are we trying to prove? So ZKVM, as opposed to ZK in general, the thing that we're trying to prove is state transitions for a computer, right, a virtual machine. So this is a universal ZK circuit that can perform any computation. So in this context, zero knowledge means that you wouldn't reveal any private inputs used to make that computation. Maybe you have a secret key and you're signing something, for example, as well as any intermediate states of the computation. I said these first 2 points already, but ZK is wonderful. It's really exploded in the last couple years in performance. It's still much too slow. It's also difficult to use. Cryptography is hard, and there's, you look at any leading ZK system, there's like every company has their own fork of it, and the docs are like from 6 generations ago, and it's something that tends to take a long time to on-ramp on. So this is something that a virtual machine might help with, because you can write programs in C or something and then just run them on our machine, and we do the ZK for you. So you don't have to write circuits, you don't have to spend time getting people at your company to learn the cryptography. You can use this system, and it's universal. I think I'm going to skip most of the text on this slide, but when you try to say universal circuit, prove any computation, what does that mean, right? There's any number of things are Turing complete, including Magic the Gathering. It's a fun fact I recently learned. And so some of the different approaches you see are, some people have a domain-specific language. This tends to be difficult to use, but lets you be very precise in the circuits you create. On the other end of the spectrum would be using a standard instruction set, so something like RISC-V. This is what a lot of other teams do. This is great because it's an existing computer architecture that models real-world computers. There's good compilers for it already. However, that instruction set is optimized for being good on actual silicon computers, not necessarily for zero knowledge. So the approach that we take with Valida is a little bit of a compromise. We have a compiler from the C language, which will in the future support C++ and Rust, into a custom machine architecture with a custom instruction set. And that's designed to be very efficient to prove. I think this is probably one of a couple design choices that we made that gives us the performance edge that we have right now. So I hit on this a little bit, but I think one of the real reasons that ZKVM is a good choice to use in an application is that you don't have to worry about security flaws. You don't have to worry about learning cryptography. It's just something that you can use that gives you these properties. Yeah, so some of the other systems out there, I mentioned sometimes how are hard to use. You have to use a domain-specific language. Another thing that I'm excited about with Valida is that, as a cryptographer, when I started thinking about ZK, 3 years ago or something now, the field looked entirely different. We're thousands of times more efficient than we were then. And there's no reason to believe that this is going to change anytime soon. So, we have great performance today. That's wonderful. But a year from now, everybody's going to be using different cryptography than we are now. So an important design philosophy for Valida is that we want everything to be super modular. Each separate cryptographic piece should be able to be swapped out independently from one another. And this is not the case in some of the production systems out there. Something like RISC-0 burns in a few cryptographic choices that are a little bit hard to change. So here's a pipeline of how this design goes. There's much too much content in this slides to go over it, so we're going to stop a little bit early. But yeah, I talked about designing the instruction set architecture. So what are you proving, right? And then you need to, in order to not have developers have to use an unfamiliar system, that puts the onus on us to create a compiler for that specialized architecture, which is a major part of what the Lita Foundation and the Valida project are about. In the future, we might do things like hardware acceleration with GPUs, formal verification in the sense of theorem proving like lean or something on the critical components, because we hope they will one day be used to secure billions of dollars in assets. Yeah, so here's a schematic for the flow I was describing, right? We go from, on one end, your normal program, write in a language you like C. You compile it. You have to use our compiler to do that. That's a major project for us, and that gives you, some sort of assembly code that is specialized for our use case. And then that, from there is when we use cryptography to prove that the machine executed the given machine code correctly, and that gives the right output. I think I'm going to skip some of the details of the mechanics of the proving, but the proving part is actually less unique to Valida than some of the other parts. We use Plonky 3, which is the best ZK prover out there right now. It has really amazing performance. It's also a really nice library that's very extensible, very nicely written code. So it's a little bit more mature. Came out more recently than some of the other systems. This is based on Starks. If that helps explain what that is, I probably won't say more about that. So, okay, another design principle that makes Valida really fast is that we separate the computer, right, the virtual computer, like you do in an actual computer, into a series of chips. So one chip does the main instruction loading, writing down the memory accesses, incrementing the program counter, stuff like that. But then we have a separate chip to do arithmetic. We have a separate chip to do bitwise operations. We have a separate chip to read input and output. And this architecture can also be thought of as based on lookups. If people have heard some of the hype around Jolt. That's one of the design principles that made Jolt really effective, is that they tried to use as many lookups as possible. We don't really state it like that in our documentation, but you can think of the way our chips communicate with each other as being a lookup argument. So this means that you don't have one big circuit that has to handle everything, and then it has to, allocate space for each of the chips at each step. Instead, we have, but by this separation into different chips, for example, the arithmetic chip only needs to pay for the arithmetic operations you actually do, rather than paying for arithmetic options in every computer cycle for every possible arithmetic operation. I think the most interesting one of these chips is the memory chip. There we have an additional lookup argument to make sure that the memory is consistent with itself, that you have read-write consistency. I think that's all I'm going to say about this slide. Here's a diagram of how these connect to one another. Like you would have in an actual silicon computer, right? We have a series of chips. Each one of these chips is a ZK circuit whose execution is proved, and then they communicate with each other through a series of buses, which are a metaphor for lookup arguments. They can be read-write or write-only, and then we can address memory in the usual concept of memory consists of a series of words. The words are bytes. We have to make sure that the bytes are actually bytes, so that they actually fit into 8 bits, right? When they're represented by a finite field element or something. And then we also, so our custom instruction set architecture lets us optimize the architecture of the machine additionally, so we get rid of registers entirely. Right? Why do registers exist in a silicon computer? It's because electrons need to move actual distance, and it's much faster to address a register than it is to look up something to main memory. That concept doesn't make sense in the ZK world. It's everything is theoretical, everything is math. So in our architecture, it's no harder to address main memory than it is to address registers. By getting rid of registers, we're able to make the circuit a lot smaller. So the only registers we have give us the frame pointer and the program counter, which say where in memory local variables are stored and where in memory the next instruction is stored. All other values that are part of the computation in a given step are given by memory reads and writes. So the way you would use this in an application is that you'd first run your program on our virtual machine. This will generate some sort of trace that tells you, following through each step, what the intermediate states are, as well as maybe some auxiliary information that you compute to aid the prover. Then you give this to the prover. This is the cryptographic piece. This is Plunky 3. And the way that the prover and the VM talk to each other is by a series of polynomial constraints. So you write down a bunch of polynomials that express that a given set of values is the correct state transition from the previous one. And then the thing that the VM passes to the prover is this set of intermediate values, the machine state at each step. And then that's when we switch to using zero-knowledge cryptography, Stark's, Plunky 3, to prove that the prover actually knows a valid, one word that's used here is witness or trace. Then this creates a short cryptographic proof. This is just the output of Plunky 3 is going to be tens of kilobytes. That can be compressed further using additional layers of ZK if you want to put it on chain or something. There's more or less standard techniques for that. But then this can be passed around, and anybody can look at it at any time in the future without any permissions and be able to verify that the computation was performed correctly. So one important piece here is that we use a very efficient field. So this is called the baby bear finite field. Its size is very close to a power of 2, and the difference between its size and that power of 2, 2 to the 31, is also close to a power of 2. So this means that to compute operations in a finite field, you compute them as integers, and then you have to reduce mod p. And reducing mod p, because it's close to a power of 2, is something that your computer, which uses binary arithmetic, can do efficiently. Another point here is that this field is not giant. It's a 31-bit field. This is, right, you need something like 128 bits of security in order to achieve that. In other settings, you need to use a 256-bit field, whose arithmetic is obviously much slower. We're able to get around this in Starks. This is a general property of Starks, by having two different fields come into play. There's one that you use to write down the states of the machine, the constraints between them, but when you go to the actual cryptographic operations, so challenges from a verifier, stuff like that, you use this extension field. This is the unique degree 5 extension of this finite field. Every finite field has a unique extension of each degree. That's a fun algebra fact. This one can be generated by adjoining a fifth root of 2. So then the general architecture of how you turn this into a proof is that you represent your trace, this record of all the intermediate states of your computation, as a bunch of polynomials. And you use what's called a polynomial commitment scheme to produce short records of each of the vectors that you have in this table. This is a common piece of design for almost all snarks in existence today, is that you have kind of two separate parts. One is representing things as polynomials, computing short commitments to them that you are later able to efficiently generate proofs that the polynomial evaluated at a given point has a certain value. And then you use a separate piece of argument to turn this low-level cryptographic primitive into a proof that the state transitions are correct. Okay, I've said some of this already. I talk more than I click, I think, but we have one execution trace per chip. This is an important piece of the design that I think is this plus the custom instruction set architecture are probably the two things that really make our performance as good as it is. And then there's a standard way of encoding the trace, which is some sort of matrix. Each column of the matrix is a vector, and there's a standard way to encode this as a polynomial using polynomial interpolation. Don't need to worry about the algebra for exactly how to do that, but that's a thing you can do. And then you can commit to these polynomials, and later on you'll be able to say that you'll be able to quickly generate proofs that evaluating the polynomial gives you something. Okay, so we have to pay somewhere for this design where we have a bunch of separate traces, right? Each chip's internal operations are now verified, but then we also have to make sure that the chips are talking to each other correctly. For this, we use what's called a permutation argument. A related idea is a lookup argument, which are very popular right now. So there's a separate trace that is a bunch of intermediate values needed to do this permutation argument, which is a kind of lengthier algebra thing. And the important thing is that you have to compute these after you compute the main trace and commit to them, because they depend on random values which need to be conditioned on all of those. Okay, so yeah, here's maybe a little bit further of a breakdown. So each column is one of these polynomials. Let's have yeah, nice. Each column of the trace is polynomial P0 through Pn. The way that these relate to the vector, by the way, is just like evaluate this polynomial at 0, you get the first element, evaluate it at 1, you get the second element, and so on, for a given vector. So it's a pretty simple thing. Then you can do a trick where you combine all of them together using powers of a randomly generated number. when I say randomly generated, what this means is that you have to take all of the prior values, hash them, and then the output is considered to be the random element used to make this combination. Because the prover doesn't get to pick this element, it's a hash output, which, as sort of all a blockchain is based on the idea that hash outputs are essentially random. This means that if I can prove something about this combination, then the only way to do that is to prove it about each column separately. And then in order to show that the constraints vanish, so we have a bunch of constraint polynomials that need to be 0 in order to say that the state transitions are correct. What we do is we show that the prover knows this quotient. So basically, there exists some q such that z times q equals p, where z is the smallest polynomial that vanishes on each of the points you evaluate on, so 1, 2, 3. So such a q exists if and only if p is 0 at each of those inputs. So the prover, by proving that it knows a q with this property, is able to show that the polynomial vanishes on each input, which is the goal. Okay, you do this once for each chip, and then later there's a second similar argument that shows that the chips are compatible with one another. So we use Starks. Starks are used in pretty much all of the best ZK systems around today. This is different than it was a year and a half ago when everyone was using elliptic curves. 2 years from now, we might all be using lattices or something. Like, this field changes very fast. But right now, Starks are really great because you don't have to do any expensive operations with elliptic curves. You don't have to use really large fields, and the basic cryptographic operations you have to do are just hash functions, which can be computed really quickly on real-world hardware. An important technical point is that we make sure that the constraint polynomials have degree at most 3 everywhere, because the degree of the constraint polynomial is an important factor in the total cost of proving. I talked about this field already. We might also switch to this Mersenne 31 field, which has even faster arithmetic on hardware than Baby Bear. The reason we can use that field now is based on a recent cryptographic advance called Circle Starks. Okay, I think that's all I want to say about the prover, but let's look at the compiler a little bit. So we use the LLVM project, which is this wonderful open source generalized way of representing the result of compiling. So it's kind of a universal machine code that can called an intermediate representation that remembers more information about where functions are defined, where variables are defined, that sort of thing, than actual machine code does. But it doesn't depend on the source language. This is something that has been around for a little while, has a really big community around it. A lot of engineers working on it already, so it's a great system to use for us. And then, I'm the cryptographer, not so much the compiler person, but the pipeline for compiling, you go from this LLVM representation, and then you have a series of steps of transforming this into machine code for our custom instruction set. Okay. So for front ends, right now we only support C, but we will in the near future support C++ and Rust. You compile it using the compiler that you already have into this LLVM intermediate representation. So for Valida, we really just start at this level, and we optimize the intermediate representation and convert it into our backend. So this means that a lot of our work will be somewhat language independent, so we can use a lot of what we did on our C compiler for our Rust compiler. everything is very customizable. The idea is, if you want to use Valida, you can define your own set of chips. Maybe you do some sort of hash function a ton of times in your computations. So then you can have the benefits of the VM. It's a little bit easier to use and stuff, but you can write a custom circuit for your hash function or something that might run faster than executing the VM would. And then the way the software is written, it's pretty easy to extend in this sort of way. Other people use the word precompiles here. We think of it in terms of these chips, but they're equivalent. Everything is very open source. Here's our GitHub. You can see, all of the current issues. There's several things that we need to fix right now. This project is, in an alpha stage, and we very much welcome contributions, et cetera. We have an Apache MIT license. Okay, yeah. So I showed you some of our benchmarks at the very beginning. This is a number salad of this spreadsheet that we use to compute these benchmarks for the Fibonacci sequence example. But we're getting really great performance so far. Our system is in an earlier stage than some of the other systems out there. There's further development, which means we probably have room for further optimization. But as it stands, we're already hundreds of times faster than, for example, RISC-0, which I think is probably the most mature and well-developed VM around right now. There's also newer projects like Jolt and SP1 that are pushing the performance a little bit higher, but so far they haven't beat us, which is really exciting. Those projects are wonderful. They brought a lot of really cool new ideas into the field. We have a lot of ideas on how to make this even better. For example, multilinear Starks, circle Starks. Probably one of the really big places where we'll be able to get better performance is GPU acceleration. Here's an idea of something you could build with this VM. Like you have this template thing, lets you create code in your IDE, like a Visual Studio type environment, and then just press a button and you'll get a ZK proof of it. Okay, I think I'm gonna stop there, but let me end on this slide with our telegrams. We're hiring, especially if you're a compiler engineer or a cryptographer, please talk to us. Here are our telegrams. I'm Tesseract. And wait, there was, yes, that's the end. Great.
Thank you so much. There's still time for a question or two if anyone has one.
Yeah, so you were talking about your own chip and you have like a super modular ISA design. So you also going to produce your own chips then, or you want to work with the hardware manufacturer or something?
That's a great question. There are a lot of different kind of parallel ideas in this space right now of how to best hardware accelerate. Of course, the issue is that manufacturing a custom chip takes a very long time and a ton of money and expertise. So the first thing we're looking at would be GPU acceleration. So that doesn't require any custom hardware. And kind of the next stage after that would be something like specialized chips for hash functions, which are most of the work that our prover does. And that will be the same for us as many other projects. It would be really wonderful to get to a state where Valida is kind of a standard that a lot of people use, and it becomes worth it for some hardware company to manufacture a chip that produces exactly our instruction set and stuff. But of course, that's a really big project. Yeah, great question. I think hardware acceleration is like where we're going to get the next 100x improvement. Like,
I mean, maybe I didn't understand that part so well, but like when you were talking or describing the ISA and you had like a RAM chip or something, was that like more a theoretical thing for the future? Is that being emulated, or like how is it? Has it been tested in practice?
Yes, very good question. So these are the chips I was talking about. There are metaphorical chips.
Okay.
So when we when we write down our the cryptographic set of constraints that computes the operation of our VM, we separate this into a series of chips. One of the things that I think is cool about ZK is that we're teleported back in time to the 60s where we're inventing computers and stuff, but we get to do it again, but with math instead of with electrons, which is pretty rad.
Yeah, cool, thanks.
Thank you.